Hello, everyone. Good morning. So as Andrew described, I guess I don't need to talk about my background anymore. So apart from the RI project, I'm going to give you a little bit of background on what we do and what motivated us, and so that you have a clearer picture. So if, in case you're wondering, this is an image taken by a drone of our barge where we're working here, really. People are moving, if you can see. I'll start with that. So what is the goal of Waves Lab, as we know? So when we started back, when I joined in 2009, so our goal was to make tools, autonomous tools, to support scientists so that they are able to collect their samples from traditional method to completely autonomous systems, so which will enable us as scientists to collect data more efficiently. Now, that's a few years back, what we're talking about. But then, what is the ultimate goal, or what is the dream of an engineer? So being an engineer, you might find my talk a bit of unorthodox, because my talk has more engineering component predominantly than science ones. So I have extensive usage of images and videos. I apologize if it offends you. Anyway, moving on. So these are some traditional vehicles that we started with, some surface vehicles, regular kayaks fitted with computers, motors, etc. And the very common hexcopter, in this case quadcopter, or commonly known as drones, and autonomous underwater vehicles, the submersibles. So another focus of Waves Lab recently been to make them robust, make them low cost, and also efficient at the same time. So we are constantly working on that to make our vehicles to have these qualities, if not all, as much as possible. So these are some efforts we've been through. So these are small kind of snapshot what we have been doing last few years. So on top, you'll see a small robot that made out of a live buoy, and which is pretty economic. It's very low cost, I can tell you that. And they're robust. And we have drones. They can land on water. I have some videos that I'll share with you. And last not but the least, the RI project that Andrew introduced. And I'm going to talk about a bit more about that. So this is a small video. So this is a robot that we just put up together, and we claim this fairly robust. You can hit up with a running speedboat, and it still works. You'll see in a moment. It still runs. It just was confused, getting hit by a speedboat. And next, we have a drone we have developed, we'll say assembled, that can land on water. So we had incident before, drone getting damaged by seawater. So this is one of that. Now moving on to the project that we're talking about, the RI project, RI-funded project. Now I'll start with thanking Smart Management, because this was a great opportunity given by Smart and the Research Initiative Project, where they allowed us, individuals, to grow and develop the whole funding cycle capability. I mean, to enable us to learn the process of complete funding cycle. I'm talking about writing proposal, getting peer reviewed, get the funding, and also, the most important part, delivery, the results. So Thank you for that. And so this is one of the a project that was funded in 2015, and it was renewed for one more year in 2016, that is this year, and it will end till, I mean, the project is till 2016. So this is a commonly can be mistaken as Argo float, which it is a bit like an Argo float, but we have added some extra features. So I'll start with some field deployment photos that we built and we have tested, in case you were wondering. So if you know an Argo float, which works as a floater, imagine if we let it go in, Johor Strait, so it doesn't have any control of its own. So they usually tidal current driven or current driven vehicles. So we have taken the concept of an Argo and modified a bit with some extra landing capability. And so in a normal condition, our Argo will float, will travel in water column, measuring all the parameters. And frequently, it surfaces up, transmits data to the remote station, and then keep swimming. But so what we did with our float is we added a capability to control its movement. So in case of an adverse condition, so if you detect you're flowing away where you're supposed to be, then you get a GPS log and you land yourself to safety so that you wait for the condition to be reversed. So as a result, what we get is we can control with some prediction of current that where we want our vehicle to be. So these are some data that we have collected. I'm not going to go through all, but just show you one. So this is a validation of our depth versus temperature and the state machine, which suggests that it's working. It's really hard to see in Singapore water if you have been there. So that's all. And I would like to thank all of our team members, and especially collaborator of the submersible project, Professor Chitre from NUSARL. And I would love to take some questions. Thank you.
Questions? Jim.
So the goal of the float then is to more or less stay in one of those high current environments, so sort of catch the tidal currents?
Yes, the question is if the goal of the float is to keep its position in a controlled manner. Yeah, so the idea was to use the tidal current as the propulsion system in a coastal area like Singapore, and keep it, like a geofenced area, and keep it inside that fence.
So is there a control algorithm, maybe in a poster we'll find later on how that works?
We are currently working on that, but there are some work that we have presented, maybe not on poster, but there are some simulations or basic, current prediction model that we're working with, so which helps us to keep things in position.
So it has a current model on board that it uses to time its ascents?
Exactly. For now, we have a coarse model. We don't have a pretty accurate model for now. So we just basically look at tidal current, amplitude of that in specific locations. But we want to do that like a 3D current model and include that in the vehicle in future.
Okay, thank you.